Hello, in this video we study linear dependence and linear independence. Okay, before that, let me remind you the example we considered in the previous uh, video. We consider R2. In that R2, we have two vectors, 1, 0 in here and 0, 1, right? And we know that any vector in R2 can be represented as a linear combination of these two vectors. Does that make sense? So, you know, uh, if I add one more vector, let's say add one more vector in here, like it is negative 2, 0. So let's say this is E1, this is E2, and this is E3, right? Uh, and if I consider the set S, have E1, E2, and E3, right? So that means, in this case, S is also spans the whole R2. Does that make sense? Because any vector can be represented as a linear combination of E1 and E2. So, you add one more vector, which is better, right? But sometimes you think that is better, but sometimes that is not better, okay? But that is the main purpose of this video. So you say, yeah, actually span S is of R3, but at the same time, if you have S prime, that is just E1, E2, right? And then you also have span of S prime is also R2. So what is the difference between these two guys? Of course, you can see that actually S prime is better because you have less vectors, right, than in S. And each time when you solve a system linear equation, you have the coefficient matrix, of the size less than the coefficient matrix with respect to E1, E2. Do you remember that? Because you need to write when you express a vector, right, as a linear combination of E1, E2, E3, you need to solve this system E1, E2, and E3. This in the column forms, right? And here's your vector U. But if you solve the same, right, but with respect to S1, S prime, you would get, the following matrix E1 and E2. And here's your U. Because the second system is easier to solve. Or I can say it's cheaper to solve. Cheaper. In the sense that, computation is easier. Does that make sense? So from this example, we have the following natural question. If you have a spanning set, can we get a smaller spanning set? Right? Why you don't change the linear span of that set? Okay, let me summarize this. So you have a set S. For set S, you have a linear span of S. Okay. Then the question is, let's say this is V. The question is, you have subset of S. This is subset of S. And you also have span of S prime. And these two guys equal. So that is kind of, in order to find S prime, we need to solve some optimization problem, right? Does that make sense? So find the smallest one, okay? I will write here the smallest one. The smallest, subset. The smallest in the sense that if you just remove one vector from here, you will not have the linear span of the original set. Okay? So, in that situation, we will talk about linear independence. Okay? So let's say this. In this picture, three vectors, E1, E2, and E3. This set is linear dependent. Why? Dependent because E3 can be represented as linear combination of E1 and E2. Does that make sense? Because E3 can be represented as a linear combination of E1 and E2. That's why this guy S is linear dependent. Why S prime is linear independent? Why? Because E1 cannot represent it as a linear combination of E2. And of course, E2 cannot be represented as a linear combination of E1. So such set is called linear independent. So from here, in order to solve this question, you might think about, let's define independent and linear independent sets, right? And if this set is already linear independent, so that is already smallest one. You cannot remove any vectors from that, and you still want to keep the linear span of that. But if the set S is linear dependent, that means you may remove some vectors like this from here. You may remove E3. You still have the same linear span. You see this? You still have the same linear span. So that means from a linear dependent set, you may remove some vectors to get linear independent, and you don't change the linear span. But before we move to examples, I would like to give definition of linear dependence and linear independence. So suppose that you have some vector space V, and S is a set V1, V2, and Vk. The set S is called linearly independent if the system C1 V1 plus C2 V2 plus so on plus CK Vk, it should be CK Vk, has only trivial solution. That means only zero solution. Otherwise, S is linearly dependent. So what does it mean otherwise S is linearly independent? That means if this system has non-trivial solution, right, then at least one vector in the set S can be represented as linear combination of other vectors. So in that case, S is linearly dependent. Dependent because one vector is represented as a linear combination of other vectors. Means that vector depends on other vectors. Does that make sense? Okay, now let's consider the following example. The easiest cases are 2. So you have set S is 1, 2, 3, 4. Okay. We want to check if S is linearly independent or not. Okay. So you have U1, U2 in here. If you want to check that, you need to solve the following system: lambda 1 U1 plus lambda 2 U2, right, equal to 0. But that means you represent 0 as a linear combination of U1 and U2. Does that make sense? So you need to write this as 1, 2, 2, 4, right, in the column form. And here you get 0, 0. You have homogeneous system. Okay. From here, you don't have to solve this because the matrix is 2 by 2. So you might check this easily. The determinant of this guy is what? The determinant of the coefficient matrix is equal to 0. So that means, the system has infinitely many solutions. Right? The system has, I write here, non-trivial solution. So that means by the definition, U1 and U2 are not linearly independent. Means S is linearly dependent. Okay? So it's pretty easy. Again, right? The determinant works in this case. If you have a square matrix. Does that make sense? All right, let's consider another example. S equal to 1, 0. 0, 1 and 2, 4. Okay, so again in R2, I tell you, right? We can say right away this set is linearly dependent. Because this set is linearly dependent. Why? Because if you consider vector the system 1 0 0 1 in here 2 2 4 and 0 0 0 in here, yeah, you can see right away, you know, this is equivalent to the following one: 0 0 0 0 1 0 0 0 0, because 2 2 4 is the linear combination of these vectors. That's it. So that's why linearly dependent. Okay, so from here, as I mentioned at the beginning of this video, if you just pick two vectors in here, you get linearly independent. Does that make sense? Now let's talk about R3. So you have three vectors 1 2 3. The second one is 0 1 2, and the third one is negative 2 0 and 1. They ask us to check to determine if S is linearly independent or not. Okay, so as we just solved in the previous example, I need to write all these vectors in the column form, right, to consider the homogeneous system. Does that make sense? So I have 1 2 3 in here, I have 0 1 2 in here, I have negative 2 0 and 1 in here, I have 0 0, you know, homogeneous system. And if this system has non-trivial solution, the set S is linearly dependent. If we have only trivial solution, so linearly independent. Again, the coefficient matrix is 3 by 3. So we can check that, right? If the coefficient matrix is invertible, then only trivial solution, right? If not, means non-trivial solutions. So I can check determinant of this matrix, let's say matrix A, because we know invertibility is equivalent to the condition that determinant is not 0, right? So we check. I think we found this determinant in the previous video, but let's do that again, right? So I have 1 1 1 is 1, 0 0 3 is 0, and then 2 2 with negative 2 is negative 8, right? And then I have minus negative 6 plus 0 and put 0 in here. So basically you get negative 1, not 0. That means the coefficient matrix is invertible. Or actually we know that, the system star has only trivial solution. So that means, from here I get S is linearly independent. You see, it is pretty easy. So basically, testing for linear independence means solving the homogeneous system, and we'll see how many solutions that homogeneous system has. That's it. If you have only trivial solutions, so the set of vectors is linearly independent, yes. If you have non-trivial solution, means linearly dependent. Right? It's pretty easy. All right, let's consider another example with polynomials. So now let's talk about P2, right? A vector space of all polynomials of degree less than or equal to 2. I write here polynomial of degree less than or equal to 2. Okay, so I have the following S. It is 3 vectors: 1 plus x minus 2x squared, and 2 plus 5x minus x squared, and x plus x squared. So we have 3 polynomials, but this is vector space, so I look at these polynomials as vectors. Okay, and of course you may solve you may solve this, C1 1 plus x minus 2x squared plus C2 2 plus 5x minus x squared, and then plus C3 and then x plus x squared equal to 0, right? And you need to show that, you need to consider, if this system has only trivial solution or not. And in order to do this, you need to compile, you need to for this out and then group them, right? By terms x squared and free coefficient. So I have the following one. C1 plus 2C2 equal to 0. Okay, let's do step by step. That is free coefficient. The next one, C1 plus 5C2 plus C3. Here we have x. And then the next one is negative 2C2 minus 2C1, sorry, C2 plus C3, x squared equal to 0. And this equal to 0 for every x. So that means all coefficients should be 0, right? So you have this 0, another equation, and the third equation. So basically you have the following system. C1 plus 2C2 equal to 0. C1 plus 5C2 plus C3 equal to 0. Right? And then negative 2C1 minus C2 plus C3 equal to 0. Okay? And then you can write the system in the matrix form. You have 1, 2, 0, 0. 1, 5, 1, 0. Negative 2, negative 1, 1, 0. And then you need to check if the system has, trivial or non-trivial solution or not. We use determinant, right? We use determinant. But I think you know how to do that. The thing I want to explain in here is, when you work with polynomials, you don't have to do all these steps. You don't have to do all these steps because we know the correspondence between polynomials and vectors. I hope you still remember that. Because, in order to determine a polynomial in P2, we need 3 numbers. And these 3 numbers are in order, right? So, for example, the first polynomial is corresponding to, let me write here, 1 plus x minus 2x squared is corresponding to 1, 1, and negative 2. I just pick coefficients of this polynomial, right? And set them in the order, And the second polynomial is 2 plus 5x minus x squared is corresponding to 5 and then negative 1. And the last one is what? X plus x squared is 0, 1, and 1. So in order to work, instead of working with this polynomial, I just need to work with these vectors. And we know how to do that, right? We write this vector in the column form. You get exactly this system. Does that make sense? So you only need to, convert polynomials into vectors by taking all coefficients of each polynomial, right, and put them together. But you have to pay attention on this, right? Because sometimes I may, they may lie you, not only me, right? So, sometimes I write 1 plus x minus 2x squared. That is the first vector. The second vector I may give you like negative x squared plus 5x plus 2. So if you write, this is corresponding to 1, 1, negative 2. And the second one is for negative 1, 5, and 2. So you are wrong already. You need to keep this order. Free coefficient, term with the first, the degree equal to 1, and then term with the degree equal to 2. Does that make sense? So that is the only thing you need to pay attention when you work with polynomials. Okay? And now you have the homogeneous system, and your matrix is 3 by 3. You may check determinant. Let's say this is A. So I have 1, 5, 1. I have 5 in here. 2, 1, negative 2 is negative 4. 1, negative 1, 0 is 0. Okay? Another, I get 0. 1, 1, 1, negative 1. So I have plus 1 because that is, the odd diagonal, right? 1, 2, 1 is 2 with negative. So I will have the following one. Oh, I get 0. So what does it mean? That means it is not linear independent or linearly dependent. Okay, so sometimes we are not lucky in the sense that you're not uh, always have square matrices, because if you have square matrices you can use determinant, right, to see if that coefficient matrix is invertible or not. Like this example, you have only three vectors in M2, okay, so you still need to consider the definition. So you need to see if the following system has a unique solution or not. C1 V1 plus C2 V2 plus C3 V3 equal to 0, right? Or you can write the system, but as I mentioned in the previous video, we might convert these matrices into vectors. Does that make sense? So for this one, I have 2 1 0 and 1. This guy is 3 0 2 and 1, and this guy is 1 0 2 and 0. So I can rewrite this system as 2 1 0 1. We write them in the column forms, right? 3 0 2 1. And here I have 1 0 2 0 and 0 0 0 0. Does that make sense? And now our job is, just need to solve this. Even we don't have to solve this. We just need to see the solution set, how many solutions this system has. So I may, interchange the first and the second row, because I want to have row echelon form. Okay, so let me do this. 1 0 0, and here I have 0. I have 2 3 1 0 0 2 2 0. Let's do all together, right? I multiply the second row with -1, add to the third. So add to the fourth one, sorry. So I have 0 in here, I have 1 in here, I have 0 in here, and I have 0 in here. Right? So now I multiply the first row with -2, add to the second, right? I get 1 0 0 0 0 3 1 0 and then 0. I divide the third row by 2, I get 1 1 0 0 1 0 and 0. Okay, now okay, so you may keep this guy. Let's keep this guy. Let's do that, and then multiply the fourth with -1, add to the third, and -3, add to the second. Okay, sometimes we need to do non-standard. Okay, non-standard way. 0, I have 0 in here, 0 in here, 1 in here, 0 in here, 0 0 1 0 0 1 0 and 0. And then of course the second and the third is the same, so you might ignore 1, right? You get 1 0 0 0. And then you interchange, these two rows, the second and the fourth. So you get 0 1 0 0 0 0 1 0. And from here you can see, yeah, actually you have only trivial solution. That means, three matrices. This, or the set S, is linearly independent. Okay, so I think we can stop our videos in here. We have problems with polynomials, with matrices, with R2, R3. If you have Rn, you do almost the same thing. You just write vectors in the column forms, and you see if that system, homogeneous system, has non-trivial solution or not. If the system has non-trivial solution, means the original vectors are linearly dependent. If you have only trivial solution, means the original vectors are linearly independent. Okay, so in the next video we will learn how to get a linearly independent subset from linearly dependent, like this example. In this example we see, yeah, determinant is 0. That means one row in here should be a linear combination of other rows, or one column, right, is a linear combination of other columns. Does that make sense? And you see, yeah, actually, when you get reduced row or just row echelon form of this matrix, you can see right away the subset, which is linearly independent. But we'll do that in the next video. Bye bye.